Okay, we're going to continue rates of change for a polynomial, and this section has a really important process in it that leads straight into calculus. So the last one I did, I think, was the toy rocket, which hopefully I did it correctly. We're going to go on to this boat that leaves this dock. And they do a mix of word puzzles and number puzzles because they want you to get used to deciphering word puzzles. Okay, let's have a look at this. The distance of a boat from a dock, okay, this distance of a boat from a dock is measured in distance based on time with this formula. First of all, let's look at this formula. If I expand that, I'm going to be left with a t squared, something, 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 and this is clearly a t squared with a number in front of it. So we get a t squared times a t squared. What's a t squared times a t squared? A t to the 4, which means, since this has a positive number in front of both of them, we're talking about something that's going to do this. Now, if we look at the graph, they're probably only concerned with this part of it. So we have to sort of figure out a couple things. It helps to figure out a couple things about the graph. Now, fortunately, they gave it to us in factored form. We can see that the t is squared, and we can see that when t is 0 here, the whole thing will come out to 0. So we know it goes into 0, 0. We can also see that when t is 8, this whole thing becomes 0, meaning the whole result will be 0, which means it comes back to the x-axis at 8. It also, the t squared and the t minus 8 squared tells me that the graph is going to bounce and touch and then come up and then bounce and touch and then come up, because that's what the t squared. Now, sorry, that drawing here isn't very good. I'll just do it again. There. It also tells me, because there's only 2 points of intersection and they're a nice equal distance apart, that this side and this side, everything's going to be balanced right in the middle. And I can tell right in the middle is 4. So I can even figure out the max point here. And the reason I know it's nicely balanced is because this side of it will pull up just as much as this side of it will pull up, which will cause the max right in the middle. It would be different if it was just a triplet, a cubic, because that pulls more on this side, so it's not quite center over here. It pulls more on this side, so it's not quite center over here. But when it's to the 4 or to the power 6 or to the power of the 8, and you have something like this, it mirrors perfectly in the middle point. So I even know the farthest point it is from the dock. Now, since y, or d of t, measures distance, I know that this represents distance away from the dock. Therefore, the x-axis represents the dock, essentially. And I can tell you that this here represents t, time, which is in minutes, and distance is in kilometers. Okay, it's quite clear. They also put a domain restriction, 0 to 8, so they're even only concerned about this part of the graph. That part of the graph. So that tells me that the boat left the dock at 0 time, went the furthest at 4 minutes, and came back after 8 minutes. It also tells me it hit a max there and has a couple mins here. It's really a lot of information. Sketch the graph. So we did. Estimate when the instantaneous rate of change to the distance of the dock is positive, negative, and 0. So instantaneous rate of change is simply the slope of this graph. So I can see that all through here, after 0, but not including 0, it's positive. Right? Positive there, positive there. Not at the 4, though. I can see at the 0, put that back to red, I can see at the 0, the rate of change is going to be flat, 0. And I can see at 4, the rate of change is going to be flat, 0. And I can see at 8, the rate of change is going to be 0. So right there, I've identified my positives and my zeros, and now I'm going to identify my negatives. Well, after 4, but all the way to 8, but not including 8, it's clear the slope is negative. And slopes are negative essentially when the line is facing down, and slopes are positive when the lines are facing up. So there we go. We can clearly see this. So when is it positive? When 0 is smaller than x is smaller than 4. When is it negative? when 0 is bigger, sorry, when 4 is smaller than x is smaller than 8. When is it 0? At x is equal to 0, comma 4, comma 8. That's when it left the dock, started turning around. 4 represents when it, just before 4 it's leaving the dock, after 4 it's coming back to the dock. 4 represents the maximum distance from the dock. What happens to the boat when the instantaneous rate of change in distance is 0? Well, it's either leaving the dock, turning around, or arriving at the dock. What does it mean when the boat's rate of change of distance is negative? It means it's returning to the dock. The slope is coming back to the dock. When it's positive, it's leaving the dock in this particular case. Number 12. Approximate the instantaneous rate of change at the zeros of the following function. Okay, so it really depends whether those zeros go through the x-axis or bounce on the x-axis. I can see right away that it goes through, let's change to black, 0, comma 9. Because when x is 0, this is all 0, and this is left with minus 9. So right away I can see it's going through 0, comma, minus 9. That helps. I can also see it's a positive cubic, so it's going to sort of do something and go through that point. So let's see if we can figure out some factors using synthetic division. The number in front of that x4 is this, the x cubed is this, the x squared is this, the x is this, and the number is this. And I can see all the x cubes and x squareds and x's are represented. Let's try the simplest thing first, 1. And it's synthetic division is the same thing over and over again. So we drop the 1, we multiply it by 1, we add it to the minus 2, we multiply that minus 1 by 1, we add it to the minus 8, we multiply that by 1, we add that to the 18, we multiply that by 1, and when we add it to the number, if we get 0, it's a factor. Well, it is 0. So that means x minus 1 is a 0. Now, I'd be tempted to do the 1 again to see what's left, because here I've got minus 1x cubed minus 9x squared plus 9x. Oh, let me try that again. 1x squared minus 1x cubed minus 1x squared minus 9x plus 9. Like that. Cubed, squared. Now, we're going to get rid of these. I'm going to try 1 again just in case, because these numbers look very similar. The new coefficients in front of my x cubed, x squared, x, and my number are those. If I drop the 1, multiply by 1, I'm left with this. Oop, left with 1. I get a 0. Multiply it by 1, I get a 0. Minus 9. And look at this. Multiply it by 1, I get minus 9. Add positive 9 to minus 9, I get a 0. So I can see that x plus 1 is indeed a factor twice. Great. What am I left with? I'm left with x squared minus 9. Well, that's a difference of 2 squares, x plus 3 and x minus 3. Great. X plus 3 and x minus 3. And I'll just do that and get rid of the other one. There. I figured out all my factors using synthetic division. Let me do a rough graph. Even though it doesn't call for a rough draft, the rough graph will show a couple things of interest. First of all, it bounces down by 1. It goes through minus 3, and goes through positive 3. So it's going to come down. It's going to go through here. It might even reach a peak lower than that, because it's probably on its way up. When it bounces on 1, comes down, and goes through 3. So this represents minus 3, 0. This represents over here 1, 0, and it definitely bounces because it's squared. And this represents 3, 0 on the right side. As soon as I push it over, 3, 0. It's quite clear that the distance between this and this one is 4, and the distance between this one is 2, which tells me that this will be a lot lower than this. It's just the nature of them, so I even didn't draw it properly. So that tells me that I'm probably dealing with something that looks closer to see if I get it right this time. That looks closer to something like this. Going way down, coming up and going through the y-axis, bouncing, going down like that, and coming up. This is probably half the distance of that, roughly. It also tells me that there's going to be more pull this way for this minimum, and more pull this way for this minimum. Since there's 4 distance, the minimum is going to be to the left of minus 2. So it's going to be about minus 2.1. And the minimum here, since this is 1 and this is 3, would normally fall around 2, but a bit to the right of the 2. So it tells me the minimum is going to be about 2.1. And this over here might be minus 2.2 or even 2.3. It's going to be pulled way more to the left here. Okay. At the zeros, we need to estimate the rate of change there. At this 0, the rate of change will be 0 because it's bouncing. So at x is equal to 1, rate of change is 0 because it bounces. I'm going to suspect that the rate of change here is going to be much bigger negative, probably double, as the rate of change here, which is positive, will be. And it also helps to graph it to see what to expect. Okay. How do we do rate of change now? Well, we're going to skip that. We're just going to put that over here. And we're going to look at what rate of change, what's a faster way? You could probably take an average rate of change on either side of it, which would be a faster way of doing it. Because if we're going to do the plus x and plus h method, it's going to take a while. So let me do both ways. Rate of change for the first function would be x plus h minus 2x plus h cubed, right? Minus 8x plus h squared plus 18x plus h minus 9. And then you'd have to subtract, in brackets, the entire function here. Well, I can tell you that expansion will take a long time. And so what we're going to try to do, I will do that expansion just to show you, but also be aware it can be very full of mistakes. And it's good to use Desmos or a calculator instead of doing this by hand. But I'm going to say, just for ease, I'm going to find the value just to the one left of minus 3, which is minus 4, and one to the right, which is minus 1, and I know that's before the peak. And I'm going to take the average rate of change just to get an estimate. Okay, so that's when x is minus 4, when x is minus 3 or 2, I'm going to find the y values, and I'm going to do essentially a slope. All right. When x is minus 4, 4 to the 4, it will become positive first of all, will become 16, 64, 256. You can see how the calculations are going to be tough. X to the 3 is 64. So minus 2 times 64 is minus 128. Right away I can tell you that's going to be 128. So let's just do that right now. 128. Minus x squared, so that's going to be minus 8 times something positive, is minus 8 times 16, which is 3264. Well, this is interesting. Looks like it's coming out as 0. So, oh no, it's not. Okay, so minus 8 times 4 squared is minus 8 times 16, which is the same as minus 2 times 4 times 16. And 4 times 16 is 68, so 2 times 128. So we can see we get minus 128 again. And it zaps this last mod. So really all we're left with is this last part. And we get 18 times minus 4, which becomes minus 36 minus 72 minus 9, so minus 81. So my y there is minus 81. 2 will be a bit easier. So I can see, well, why is it minus? If it's going through there, it should be positive. So there's a good example of calculation error. So I'm going to turn off the actual graph. And I'm going to just have it calculated for me. Minus 2x cubed. Because normally I'd have a calculator. And it's always smart to learn how to program the formula into your calculator to punch in these values instead of doing what I did and do it by hand. Because as you can see, you can get errors. Okay. And I'm going to take minus that, 175. So it definitely did a calculation error. So 175, and I knew it should be positive because it was left of the x-intercept. And I'm going to do minus 2, which will be negative. Minus 45. How did I know that? Because minus 2 is to the left of the x, to the right of the x-intercept, so it's in the negative zone. And minus 4 is to the left of the x-intercept, so it's in the positive zone. Now, to do an estimate, I just do delta y divided by delta x. So it doesn't matter which order so long as you keep the order consistent with their x values. Minus 45, right, is the same as plus 45, which is 220. X minus 2 minus 45, so that would be taking the same value that I took for this, has to be the same x bound below, minus 2 is plus 2. It's minus 43. So right there I can estimate much faster that the slope is going to be negative 5.1. Big estimate, right? So the rate of change is equal to probably that, close to that. Now here's how you'd have to do it using h. Right? And try to remember that this is going to be to the power of 4. This is going to be to the power of 3. This is going to be power to the 2. And this is going to be just 1. We're going to leave some of these just as numbers because we're looking at minus 3. That's the instantaneous rate of change as it goes through minus 3. Keep in mind all this is going to be divided by h. And we'll take an h, a simple h of 0,01. Okay? I'm going to leave some of these just in there as numbers. And I'm going to convert them. I'm also going to space them out a bit. And I'm going to convert them as needed. Okay. Over here, we're going to take minus 3 plus h, right? Essentially that over and over again. Okay. Also keep in mind that this part here is all in the minus bracket. Very important, because this minus will affect every single symbol over here. So it's clear this is going to be positive, and this minus will make it minus. It's clear this is going to be positive. Oh, not yet. I got to put the numbers in there. So it's clear that this will end up being positive, so it'll become negative. It's clear that this will be also positive because this is negative and this is negative, so that's positive, but it'll end up being negative. Clear that this is negative, so it'll end up being positive. So you've got to keep that in mind. This minus will really affect all the resulting symbols. Now let me get the numbers in here quickly. There, you can see how many mistakes you can make and why I love using instead, I'll take this, the calculator that I developed and shared with you. Instantaneous rate of change. So I can just put in my formula here. Let's see if I get it right. Yeah, and I got to do it without that. There we go. And it's going to calculate my rate of change if I set my A to whatever. But let's see if we do the calculations correctly. And by the way, it looks like I got my original estimate on the other side incorrectly. So I'm going to do this all by calculation. Okay. And it's a pain. It'd be great if we could come up with a formula instead, wouldn't it? And that's what the book likes you to do. So I'm going to take 0.29999. I'm going to add that into memory, and I'm just going to put that to the 4 because a minus, and actually there I'm going to add that to memory, because a minus cubed is going to become positive. And I'm going to do minus 2 times my memory to the power of 3 and hit equals each time. And I'm going to do minus 8 times my memory to the power of 2 and hit equals. And then I'm going to do plus 18 times my memory equals, and then I'm going to subtract 9. And I get this. And you better hope you didn't make a mistake, right? I get that. Now you have to do the other one. Now I have to do the other one. And I'm going to put in brackets, and we're going to come up with each thing. So, minus 3 to the power of 4 is 9, 27, 9, 27, 81. Positive. Negative 3 squared is negative 27 times negative 2 is positive 54. Negative 3 squared is 9 times minus 8 is minus 72. Negative 3 times 18 is minus 54, 54, and then minus 9. Now, to apply this, I have to change all the symbols. To get rid of this bracket, I have to change all the symbols to the opposite. That's what the minus does. So, I'm going to clear my memory and put that in as my new memory and hope I didn't make a mistake. I've got minus 81, minus 54, plus 72, plus 54, plus 9. 0, which makes sense because remember, and I should have just remembered that, minus 3 goes on the x-intercept. So that was kind of a waste of time, and I should have just used my logic. But remember, we're all going to divide this by my h. Okay. So I'm going to take my memory, which it looks like it erased my memory. So I'm going to take 0.0959360139999, make it negative, and divide it by 0.001. And I get negative 5 0.93, which means my estimate on my last thing was incorrect. And just goes to show you got to be careful with your calculations. However, the good news is I know this is correct because when I punch it in here and make my a value, which is the same as x, minus 3, and I use an h value that's even bigger, I get exactly what I just calculated. So that means my rate of change there is -5. Great. My guess is this is going to be positive and about half of that, about 47, because its slope was going to be half as deep because it traveled half the distance between the values that this one did. So it's going to be about whatever half of 98 is. I think it's 45 plus 3. It's about 48. Positive. Now, I could go through the same problem. This time I'm using positive 3 in here. And I believe, since I know that this comes out to 0, and I should have in the first place, I could probably calculate it pretty quickly. Only this time, remember, it's going to be 3.001 instead of that. So let's take 3.001 and put it in our memory. And we're going to put it to the power of 4. And we're going to subtract 2 times our memory to the power of 3 equals, and then we're going to subtract 8 times our memory to the power of 2, and then we're going to do plus 18 times our memory, and then we're going to subtract 9, and we're going to divide that all by our h. And I get 24. Oh, it's a quarter. Interesting. It wasn't half, it was a quarter, which sort of makes sense. So it's half of the half, 24. So it's going up at plus 24. Let's see if we got that right by changing this. Our a is 3. We're taking a bit bigger h here. And sure enough, it's 24, which is great, which means we did our calculations correctly by hand. And we confirmed it with this tool. Now, from now on, I'm going to use this tool. It would be great if we had a simple formula for rate of change, and really that's what this chapter is about as well. So stick around. Estimate the interest. So here they're doing it like that. Okay. It would help if we understood this function a little bit. And here's an important one. Very important. And this one I'm going to do by hand. So, x plus 3 minus 5 are there factors that multiply out to minus 5 and add up to 3? Minus 5 and plus 1, or plus 5 and minus 1 add up to 4. And there's no other factors to 5. So the answer is no. That means you'd have to take to find the actual x values, you'd have to take a quadratic function. We're not going to do that just yet. We're going to find the value, though. We're going to say that, okay, this is clearly a positive upward facing parabola, and look, it goes through minus 5. Goes through minus 5. So that's kind of clear to me, because it's upward facing, that it will indeed cross through the x-intercept. It just won't be clean. So we're going to do instead the rate of change for when x is 1. Let's find out what y is when x is 1. Well, 1 plus 3, that's 4, minus 5. So we get 1 comma minus 1. Let's get rid of everything so that I have clean stuff. We get 1 comma minus 1. So that means this here is going to be minus 1. Let's take an h of 0.001 again. And we're going to just take this function. It's going to be that. And in brackets, it's going to be x plus h squared, which is 1 plus 0.01, which is that, squared, plus 3 times our 1.01, minus 5. all over h, which is 0.001, and minus whatever 1 is in here, which we've discovered is minus 1. Minus minus 1 is plus 1. So all we have to do is figure out the end and essentially just subtract 4, because minus 5 plus 1. So remember that this one here is squared. So I'm going to do 1.001 squared. I didn't get it right. 1.001 squared, just times itself, plus 3 times 1.001. Notice I kept it simple for us. And minus 5 plus 1. And I get that, and I'm going to divide it by 0.001, the h. And I get 5.01. So it's quite clear that the rate of change is going to be positive 5, whatever it is. We'll just call it rate of change, y per x, whatever the units of y per x are. Which means at 1, it's on the way up. It's on the way up, which means if I had to graph it, it's probably crossing over here. It's going through 0, minus 5. And it's going through 1. When it goes through 1, x, it's got a positive slope like that. Okay. Let's go on to this. Let's come up with an expression for x, but we're actually not going to take a value for x. We're instead going to say, x plus h squared. I'm going to say x plus h squared there too, or just times 3 there. Good. Minus 5, and then we're going to do minus x squared, because the minus times everything in the bracket makes it minus. Then it's going to be minus 3x, right? Because the minus makes everything in the formula that. And then the minus out front makes this positive. And that's, remember, because I had minus the whole expression, and the minus changes every sign in the expression. So you end up with that. All I have to do is expand that, subtract 5. Oh, look at this. I'm subtracting 5 and I'm adding 5. I can get rid of those right away, but I'm just going to leave them in for now so that you can see at the end. What's the expansion of this? Oh, by the way, let's replace this down here with the letter h. Now, clearly I can't replace h with 0 because I would get division by 0. But let's expand these things for fun. What's the expansion of x plus h squared? It's x squared plus 2xh plus h squared, right? I'll even get rid of the bracket. What's the expansion of 3 times x plus h? It's plus 3x plus 3h, right? And then finally I have minus 5. So the entire expansion on the left can be replaced with this. Right? Let's look for like terms. Well, I have the same term minus the same term here. Let's get rid of them. I'm left with plus 2xh, by the way. I have minus plus 3x here and minus 3x here, so let's get rid of them. I have minus 5, and as mentioned, plus 5 here, and I'm left with this. Now, what do they all have in them in common? They all have an h I can factor out, right? They all have an h I can factor out. And when I factor out an h from each of those things, what am I left with? I'm left with plus 2x plus h plus 3, right? That's when an h is divided out of each of those terms. I lose this h, I lose one of these h's, and I lose this h entirely. And I'm left with plus 2x plus h plus 3. Very good. Now notice that I have h times something, then divided by h, which means, according to my laws of math, anything multiplying something and divided by itself can be just gotten rid of. I now no longer have h on the bottom. And the question says, what happens when h becomes 0? Well, when h is 0, this is plus 0, isn't it? So I'm left with when h becomes 0, 2x plus 3. What was the number I was looking for before? It was when x was 1, wasn't it? Let's plug 1 into that. And remember that my rate of change I came up with was plus 5. Upward slope of 5. Let's plug 1 into that. 2x plus 3. Look at that. We came up with a formula that will give me my rate of change. How does this compare? How does this formula compare to my formula for rate of change? Well, notice the 2 came down and got reduced to 1. Became 2x to the 1. Notice that there's a 1 in front of over this x. It came down, multiplied the 3, got reduced to 0, so x to the 0 is 1. 3 times 1, 3. Notice there's no x here. There's nothing to do with the minus 5, so numbers don't matter. So I'm going to let you into a hint for polynomials. If I have a super long polynomial, like the one we had before, this one here, and I want to come up with a fast way to verify my rates of change, I'm going to follow that rule. For my formula that I'm going to come up for rate of change, I'm going to take the 4 down here and lower it to 3. So I get 4x to the 3. Then I'm going to take the 3 multiplied by the minus 2. I get minus 6. I'm going to lower the 3 by 1, x squared. Then I'm going to take the minus 8. I'm going to multiply by 2, so minus 16. And I'm going to lower the x by 1, x. This has a 1 over it. I'm going to multiply by the 18, plus 18. And I'm going to lower the x to the 1 by 1. X to the 0 is 1, so I just have 18. And the 9 doesn't matter. I now have a formula for rate of change for that graph. And if I'd put minus 3 into it, I will get that 96 that I got for minus 3, and I will get the 24 that I got for plus 3. Let's see if that's true. So let's try the minus 3 first. Minus 3 cubed times 4 minus 6 times minus 3 squared minus 16 times minus 3 plus 18. Well, look at that. I got my minus 96. You'll discover it will work with 3 as well. 3 cubed times 4 minus 6 times 3 squared, 9, minus 16 times 3 plus 18. Look at that. I got my 24. We now have a way of coming up with a formula for our rate of change that will really help us verify our answers and won't put us through the hell of that x plus h as much. Now, don't use the formula. Use the formula to get a good idea of what you're supposed to come up with. This is all trying to teach you to understand the relationship between rate of change and calculus derivatives. Derivatives are rate of change. They are calculus in the next chapter. But it's very important to understand it. Explain how instantaneous rates of change can be used to locate the local max or min. Well, as we've discovered, if we have a quartic, there can be up to 3 max or mins, here, here, and here. And we've also discovered that the rate of change at all the spots is 0. So if we had a formula that was equal to 0, we could solve for x and determine the x values, and thus the y values when we put it back into the original formula, for all those rates of change. We would just make our rate of change equal to 0. You can even do it for the x plus h long method, make it equal to 0 and solve for x afterwards, because you're going to be left with something like minus 96 yeah, you have to leave the x, but you'd add the h in there, then you'd expand it, and you'll be able to solve for x. You'll be left with like a general formula, like we were just doing. And you just make that general formula equal to 0. For instance, in that last case that I had, right, you couldn't do it with this one. But let's take a normal parabola. Let's take a normal parabola and find the derivative of it and see if we can come up with, let's take minus 3x, actually plus 3x minus 5, and see if we can come up with a formula, once we figure out the derivative, for the x that will be the vertex. In other words, the slope is 0 at the vertex. Well, according to me, this is our formula, right, that we come up with for this parabola. If we set that to equal to 0, we can figure out what x is when the slope is 0. Well, it's 2x is equal to minus 3. It's x is equal to minus 3.5, which is minus 1.5, which means when x is minus 1.5, we will discover the vertex. Well, minus 1.5 squared is 2.25. Plus 3 times minus 3 over 2 is minus 9. So it becomes minus 9 over 2, which is minus, which is what? Minus 4.5, minus 4.5. Minus 5, which means I'm going to get minus 2.25 here, minus 5. I'm going to get minus 7.25 is my y value when my x is minus 3. So that means that's the vertex, minus 3, comma 2, comma negative 7.25. Let's just let Desmos show us if that's true. I'm going to put in the graph. And we're going to go down to the vertex. There we go. We discovered if we can come up with a formula for the rate of change and make it equal to 0, we can solve the x value for when the peak or the minimum happens, and then plug it into the original equation to find out the y value. Now you might say, well, completing the square does that for me too, and you'd be right. I can quickly come up with my x by saying, okay, it's plus 3 over 2 squared is the completion square to create that, which means negative 3 over 2 is my x value. You're right, but this method's going to help us for cubics, which can't be factored, and quartics. We'll get more into that, even with the quadratic equation. And in university, there's a quadratic equation for cubics. Onwards. Consider this function called Euler square. Let me explain, because E will come and be important in calculus. You might say, what is E? Euler's constant. Euler's number. Well, Euler's number is nothing more than a number. It's just a specific number, like pi. Pi is a number. You always want to think of E as just a number. Okay. Do you remember your compound interest formula? You should keep it in mind, because compound interest is a very good thing any adult should know, and most adults don't know. I want to take a look at something. Okay. I'm going to pretend I give you $1. I give you $1. That's your principal. This is the result of your investment. And I'm going to give you a rate of change of 100%. What is 100%? It's 100 over 100, which means your R is 1. So I'm going to do 1. And N, as you remember, is the number of times you compound it. Well, I'm only going to compound it once. And since the N is 1 here, it's 1 here. Your T, I'm only going to give you this $1 for 1 year. So I'm going to make everything 1. So what's the middle? 1 plus 1 over 1. Your principal times 2 to the power of 1. It's clear your $1 became $2, which makes sense. I gave you $1. I give you 100% investment rate. And at the end, you've made $1, which is 100% more than your investment. Makes sense, right? Well, I'm going to keep my rate of change at 100%. This time I'm going to compound it twice in the same year. So only the N changes. T is just going to stay 1, and R is just going to stay 1. Well, this time you've got 1 times 1.5 squared. And you might say, well, that's going to give me less than 2, because 1.5 squared was less than 2 to the 1 that I had before. But you'd be wrong. By the way, we can also ignore this $1 in front and just focus on the fraction. But you'd be wrong. 1.5 squared is more than $2. It's $2.25. So that means if I compound it more, and remember this in investments, when you compound an investment many times in the year, it actually will yield better results. Well, I'm going to compound it 12. So what's 1 plus 1/12? Well, 1/12 is 0.0833. I'm going to add that to 1. And you might say, well, there's no way that 1.0833 to the 12th is going to come up with more than $2. And again, you'd be wrong. It came out as 2.61. Well, I'll tell you what, I'll make you a deal. I'll compound it as many times as you want. So you might say, okay, 365, I want you to compound it every day. 365. Okay. 1 divided by 365 plus 1 to the exponent of 365. And here's where we're getting closer and closer to this magic number, 2.71 something. As I increase this, we discover a maximum yield. It'll never go higher than 2.7. There's a whole bunch more. It doesn't repeat. It doesn't go higher than this magical number as I increase that. And that magical number is Euler's number. And that's the conversation here. It'll never get higher than that number, and that number is called E. And I want you to remember two things about E. E is equal to 1 plus 1 over n to the n as n approaches, so it's equal to the limit of this number, as n approaches infinity. That's one definition that I want you to remember. E is the number you will get when you add 1 to 1 over whatever huge number here to the exponent of the same huge number will reach your number of 2.71, blah, 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 blah. Will reach your magical E. That's one definition of E, and you should remember it. It's important. The other definition of E is I can make a magical number equal to 1 over n. Let's call it U. 1 over n. Well, here I was looking for the limit as n approaches infinity. If I replace this with U and make U equal to 1 over n, it's clear that as n approaches infinity down here, 1 over n, what does U approach? It approaches 0. So if I replace 1 over n with U, I have to replace the limit with U approaches 0 instead of n is equal to approaches infinity. So I'm going to do that. I'm going to replace this with the letter U. But wait, I have an n up above that I no longer need. What's n equal to? Well, if I swap this around, n is also equal to 1 over u. You multiply by n over 1 on both sides. You divide by u on both sides, and you're left with n is equal to 1 over u. Okay, so that means I have another definition for Euler's number, which is the same thing. I'm going to rewrite it. As u approaches, and I'll just use this. Doesn't matter. I'll use this. Approaches infinity. The formula for Euler's number is 1 plus u to the exponent of 1 over u. Let's put that into our calculator and see if that works. Let's take 1,000 for u. 1 plus 1,000. We get 1,001. And we're going to put it to the exponent of 1 in brackets, 1 divided by 1,000. Close brackets. I'm going to hit equals. And I'm going to do wrong. I forgot to add, there we go, to the exponent. And you've got to hit the brackets twice here. 1 divided by 1,000. Close the brackets. equals. Let's try that again. Oh, sorry, as u approaches 0. Sorry. As u approaches 0. It's not infinity. That's right. That's what I'm doing wrong. Because it was when n approached infinity. So that means I have to take a very small u. So I'm going to add, like h, I'm going to add 0.001 to that. And I'm going to put it to the exponent in bracket of 1 divided by 0.001, which is my u, close brackets. I get a big number. I hit equals. I get Euler's number. So that was the mistake I was making. So I get Euler's number again. So that's the two definitions of Euler's number I want you to remember. That E is equal to the limit as n approaches infinity for 1 plus 1 over n to the power of n. But you can also switch these. You can take the reciprocal of these and make u approach 0, and this is also Euler's number. This is going to be really important for derivative in calculus. But that's just an explanation of what Euler's number is. It's when I take compound interest and give you 100% rate on it and compound it 1,000,000 times, so long as I also put it to the same exponent up here as is down there. And that will always give you Euler's number. It's a compound interest maximum. And the interesting thing about Euler's number, that the reason we're going to study it, is clearly why you're going to also study this growth curve, which is just a number to the power of x. It's really the same as 2.71 whatever to the power of x, which we know will produce a growth curve. But this is a very magical growth curve. It's called the natural growth curve, and we'll get into it more later. It's essentially just think of E, though, as a number. It'll make your life a lot easier. Okay, let's go on to what this was asking. Estimate the instantaneous rate of change when x is equal to 5. Let's use our, and they're making us do the graph, by the way, of e to the x. Let's take our instantaneous rate of change calculator instead, and we're going to make f equals, and they said when x is 5, we're going to make it equal to e to the power of x. Okay, and we're going to turn on that graph. Okay, and we're going to look at what rate of change we get when x is 5. Okay, we get 148. Let's go look at that value. Let's go look at that value on the chart, see where that is. There it is. It's 5, comma. Well, what's the y value? Well, we know the y value is e to the power of x. But the rate of change is the same as the y value. Let's try it for when x is 1. Oh, we got a rate of change of 2.71. Well, what's the y value? It's also 2.71. So we have this interesting graph where the rate of change is also equal to the e to the x value. Let's try it for 2. Yeah, the rate of change is 7.38, and the value of y, e to the 2, is 7.38. So we get a very interesting graph where the rate of change, the ROC, the instantaneous rate of change, for e to the power of x, is the same as e to the x. Which means that the rate of change when x is 5 for the function e to the x is equal to e to the power of 5. It's the only graph that does this. It's the only graph where the rate of change for e is the same as the y value, or the result, of the function. And y represents the height. So the rate of change is always the same as the height of the graph if you go straight down to the x-axis. This is important later on. Consider the function here. Estimate the slope of the tangent line at 1. Use the slope and the point of tangency. Find the equation of the tangent line. Tangent line intersects the original graph one more time. Where? Interesting. Graph both the original function and the tangent line to prove this. That's a good thing to do. So we're going to forget all about E, but E is very important in later graphs, and we're going to move on to this question. What kind of function is this? Can you simplify it a little bit? You know it's a positive cubic, right? So you know it's going to go through the x-axis maximum 3 times and end up here, start here. I can factor out an x. I get x squared minus 4. I can factor this further. That's x plus 2, x minus 2. I get a lot of information out of that. Let's draw it. I'm going to have a point here at minus 2 comma 0. I'm going to have a point here at 0 comma 0 when x is 0 here. I'm going to have a point here 2 comma 0. So it's a very symmetrical graph. What's the point they're interested in? X is equal to 1. That's right here. Now, I happen to know when it's a cubic. You'd think this minimum would be exactly at 1. But because this is driving up so hard, it's actually going to pull it to the right a bit. The minimum here is going to be 1.1. Same for this part. You'd think that maximum would be at minus 1, but this part of the graph actually pulls it a bit to the left at minus 1.1, which means at 1 here is going to be just to the left of the min point, which means it's going to be sloping negatively downwards before it reaches that min point. And I just happen to know this from knowledge. You don't have to. You can graph and find out. But I know at 1, I'm going to have a slope like that's very gentle, actually. It's like that. I'm going to put it in red. But the question is, read number C. The tangent line intersects in the graph one more time. Where? Well, it's clear it's going to intersect it there. But I also want you to know something else about this. It will have the same slope somewhere else. Right there. Just to the right of the negative 1.1. So not only does the tangent line intersect, so here's the tangent line when it's equal to 1. Not only does it intersect the graph later on, right about there, but it also has the same tangent line right here, same parallel tangent line. You can discover both of these. All we need to find out is the rate of change of this tangent line, find out the formula of this tangent line. So let's go through it. Let's estimate the slope. Well, normally you would use h, but I'm just going to use my formula for x cubed minus 4x. There's my thing, and I'm going to use a x of 1. Sure enough, as predicted, it's just to the left of that. I'm going to take the value I found. The rate of change says it's negative 1, which means it's pretty much y is equal to negative 1, right? Which means the slope here is negative 1. That's the rate of change. It's going down 1y and 1x, 1y, 1x, 1y, 1x. Well, what's the formula of any line? It's y is equal to mx plus b. What don't we know about this line? We don't know it's b, where it intersects with y. We know it's down here. We just don't know where. Well, we happen to know, though, it goes through the point 1 on this graph. What is that point? When x is 1, we get 1 minus 4, which is minus 3. The point minus 3 is also a point it goes through here. 1 minus 3 is the point it goes through, which means when y is minus 3 and the slope is minus 1 and x is 1, we can figure out our b. This becomes minus 1, so we get minus 3 is equal to minus 1 plus b, which means b is equal to minus 2. We now have a formula for that tangent line. It is y is equal to minus 1x minus 2. Let's go see if our tangent line did indeed go through the x value. Oh, look at that. it went through the y-axis at -2, which is also the b value. We could have just looked at the graph, but this is assuming you're on a test without a graph. So now, it intersects with the graph one more time. Where? Well, that's when this tangent line is going to have the same x value over here as cutting through. Well, that's when this line is equal to this formula. That's how you solve any formula, okay? So that you know that when this line is going to equal the same y on the line graph as the y on this graph. That's how you look at it. It's going to be equal to the y on this graph, which means I can just say, well, it's when this formula is equal to this formula. And it's going to obviously happen twice, once here and once over here. What's interesting, though, is it's going to intersect here, but it's also going to intersect there. Well, that graph isn't going to, this particular line is not going to intersect. But we could find this line as well, which is a different line, using the same slope, and I'll discuss that in a second. I happen to know it's going to be at -1, but we're gonna solve this. Where does this line cross this graph? Here and here. Let's get it all on the same side. We're going to add 1x. We're going to add 2. So we get 0 is equal to x cubed plus minus 3x minus 2. You might say, well, I can't solve that, except that, because it's a cubic, except that we know one of the points already. We know one of the points is 1 comma minus 3. So we know one of the factors is 1, or sorry, minus 1, right? So we can figure out, I'm going to get rid of the graph, we can figure out using our synthetic division, what's the number in front of x cubed? 1. What's the number in front of x squared? There is none, 0. What's the number in front of 3x? Minus 3. Minus 3x, rather. And what's the other number? Minus 2. Now we can do our synthetic division. Minus 1. Add them. 1. Add them. 2. Add them. Minus or plus 2. These cancel out. So sure enough, when I factor out x minus 1, or sorry, x plus 1, I'm left with x squared minus x plus 2. And it's clear to me that that has 2 factors. Does that make sense? I think I should have been coming up with another x in there. It's going to come up with 2 factors, a number that multiplies out to 2 and adds up to minus 1 plus 2 is not minus 1 squared, because that adds up to minus 2. Right. So now we can set this, now we can set this equals to 0 to figure out, why does it come up with 3? How many times does it intersect the graph? Just one more time. What did I do wrong there? Let me just see. When I make minus x minus 2, I'm left with x cubed minus 3x plus 2 is equal to 0. I know that I can factor out. Oh, it's plus 2 here. Okay. I know that it goes through when x is plus 1. So I can use plus 1 here, not minus 1. And I'm left with 1, 1, 1, 1, minus 2, minus 2. There was my mistake. So I'm left with x minus 1, x squared. That should still not be plus 1x minus 2. One of these is not solvable. That's it. So now I've got to put that into the quadratic equation. 1, 1, and minus 2. And one of the numbers won't be solvable. 1, 1, and minus 2. Oh, come on. And hit calculate. And it shows me, oh no, I get x's 1 and minus 2. But that doesn't make any sense. Hang on. Okay, x minus, oh sorry, minus 2, plus 2, and x minus 1. Which, oh, I see, yeah, my bad, because it's x plus minus 1 squared. So that's a way of saying that it's just touching this one. And the other spot here is plus 2. Ugh, I really botched that up. Which tells me that when x is minus 2, it's going to go through the graph again. So let's take my original line formula, because it's easier to figure out, which was minus 1 times x minus 2. Put minus 2 in here. I get 2 minus 2, 0. So when y is 0, it's going to go through the x-intercept, essentially. And sure enough, when I look at my graph, I discover that's the case. And the square represents that it's just touching. It's just touching this spot. And just one factor represents it's cutting through. Now, interesting enough, I can also figure out where else the other tangent line increases, because it'll have the same slope as that. But I believe another question does that. But, well, we might as well tackle it. Where else will I have a tangent line that has minus 2? It's when the rate of change on this graph, and actually we won't do it, because I think another question does it, but it's when the rate of change on this graph is also equal to minus 1. Which ends up being there. Now, I won't go through how to solve that, because I think another question does. But I know instinctively there's another tangent line to both those points. Let's just go on. Sorry, I kind of botched that. Oh, here, they do it here. Okay, they do it here. 17. Determine to 2 decimal places where the slope of a tangent line and the slope of a secant line that passes through this point are equal to this graph. First of all, let's make this graph simpler on ourselves. Is it a cubic? Yes, it is. So we're talking about a graph that bounces on the 0, comes down, and then goes through 3, 0. We're also talking about a graph that has a minimum that's just to the right of 1.5. They're interested in the points 2, minus 4. So there's a point on this graph, 2, minus 4. And the points 3, 0 here. So they're interested in the secant, the slope of the secant line. Well, between 2 and 0, I'm going to guess that the equivalent tangent line is going to be 2.5x. But let's just find the slope of this line first. So we'll just put this aside. Just helps us to understand the graph and what we're looking at. How do you find the slope of the secant line? You take delta y minus 4 minus 0 divided by delta x, 2 minus 3. So you're going to get minus 4 divided by minus 1, which is 4, which means the slope that cuts through those 2 points is 4. Great. Now they want us to find the tangent line of where the tangent line with that same slope goes through this graph. Where will the tangent line go through that graph? Well, when that graph is equal to 0. When the instantaneous rate of change is equal to 0. If we take the instantaneous rate of change and we do what we did before, and we subtract this graph all in a bracket and divide it by h, what do we get? Well, I want you to practice expanding, but I can tell you that that will expand to h cubed, h squared, and then it'll be h to the cube, h squared, h, and it'll be plus 3, and you're going to learn that, plus 1. You're going to learn that from Pascal's triangle. Okay, you're going to learn that from Pascal's triangle. So I'm going to just put that aside. Forget about the h at the bottom for now. What's the expansion of this? It's h squared plus 2xh plus, x squared plus h squared. All of it times minus 3. All of it times minus 3. So I get minus 3 minus 6 minus 3. Great. That helps. Let's clean it up a bit. So I'm going to get x cubed plus 3x x squared h plus 3, and that should have been an x squared, plus 3x h squared plus h cubed minus 3x squared minus 6xh minus 3h squared. Now we can get rid of this stuff. Now what does this come out to? We get a minus 3x cubed and a plus 3x squared. Let's see if we have any like terms. I have x cubed minus x cubed. I have minus 3x squared plus 3x squared. And I'm left with this, all divided by h. What happens if I factor an h out of the top? If I factor an h out of the top, I'm left with 3x squared, 3xh squared, x squared, minus 6x, because that h disappears, minus 3h. And now I can cancel out this h, gone. Now as h approaches 0, which is the whole point of limit, this will disappear, this will disappear, and this will disappear. So I'm left with a nice formula for my rate of change. 3x squared minus 6x. Notice the relationship to the original formula. The 3 came down and reduced to 2. The 2 came down, multiplied by the minus 3, and reduced by 1. So there's a pattern here. But anyway, we have now a formula for our instantaneous rate of change. What am I looking for? I'm looking for a tangent line that goes through this graph that will have a slope of 4. the same as my secant line, right? Where how often will that happen? Well, I'll have a slope of 4 here, but look, I'll have another slope of 4 there. So it's always going to happen twice for a cubic. In other words, you're going to find 2 rates of change for a cubic. For a parabola, you're only going to find 1 rate of change that's unique. For a quartic, you're going to find 3 rates of change maximum, which makes sense if you think of the graph. But anyway, how often will this equal 4 is the question. Well, 3x squared minus 6x equals 4 is the same as minus 4 equals 0. It's clear there's going to be 2 solutions, right? Let me find, since it says 2 decimal places, it's clear that it's not going to be solved factoring. So I'm going to take my quadratic calculator and put in 3 minus 6 and minus 4. And I'm going to calculate. I'm going to make sure I got the right ones before I grab those. Minus 6 and minus 4. And it gives me 2 solutions. It gives me these 2 solutions for this quadratic. Good. That means the m is going to be 4 for 2 rates of change when x is 2.52 and when x is negative 0.52. Now, I just need to come up with well, actually, I could stop there because they don't ask for the formula of the tangent line. I can just tell you that at these 2 points, the rate of change for the graph that we were working on will be 4. Let's let Desmos do it. If I wanted to come up with a formula, I would need to know the y value because I have most of it so far. I have y is equal to 4 when x is 2.5275. To figure out the b, I just need the y value. To figure out the y value, I just got to plug that back into the original equation. What was the original equation? It was x cubed minus 3x squared. I'm going to let Desmos do it instead. X cubed minus 3x squared. And I'm going to find out when this is 2.52, almost. Oh yeah, rate of change of 4, not 5. 4. So I discover, sure enough, there's that one. And when I do negative, there's that one. Also has a rate of change of pretty much 4. Now, because it's not quite close to 4, it's because I've rounded up the point. If I take the exact value, which was, where are we? Oh. 2.52753. Oh, geez, don't do that. 2.52753. I will get much closer to 4, see? It's just my rounding error, because that 7's a big deal. And then when I take the negative of it, I get also very close to 4. So you can see, even using this, I get it. I could also take my formula that we discovered, which was 3x squared minus 6x, and I can set it to equal 4. Oops, no. To equal 4, and it will draw me 2 lines where that happens. I'll just turn off the other thing. There we go. It'll draw a red line. It'll say it happens here, and it happens again right here. So you can see that you get very, very accurate numbers. And as shown, it will draw the tangent line for me with this setup. You could replace this whole formula with the actual formula that we discovered. But anyway, this book chapter is very important in teaching you how to do these things and what it means. Chapter 4 review, we're all done chapter 4.